So this is, I think, the 20th of these workshops. They've all proved incredibly popular, and we've managed to cover a huge range of different topics. Today, I've always felt that molecules and the way they bind to proteins, there's by its nature a three-dimensional interaction, and so whilst 2D descriptors have proved a mainstay of drug discovery for a long while, it's clear that we should be looking at these molecules as three-dimensional objects. And so shape and electrostatic mapping, I think, is one of the most important features that in drug discovery. Today we have Ester giving us a talk about shape and electrostatic mapping, both from a theoretical but also as a demonstration, and if you want to, you can follow along using Jupyter or Collab, and she'll give you details of that in a little while. Just a couple of housekeeping topics. All attendees are on mute, and so if you want to ask any questions, please put them into the Q&A box, and we will relay them to Ester. The workshop is for 2 hours, but we will have a break after about 1 hour. This will give you a chance to just stretch your legs, and then we'll get back to it. And so without any further ado, I'd like to hand over to Ester and ask her to start this workshop.
Yeah, thank you very much for the kind introduction. And I'm really excited to talk today about how to score shape and electrostatic potential similarity between molecules, because I think, as Chris just mentioned, that it's a huge topic in, for example, scoring protein-ligand interactions and also beyond that. So I just wanted to start with a super quick slide about me, so you know who's talking to you today. I did my PhD in Vienna. I also was a guest researcher in London and at the University of Maryland, Baltimore. And I then spent 2 years at MIT, where lots of the work that I will be presenting today was done. And I just switched over to the Technical University of Vienna, where I am also a postdoc. And the project I'm interested in that I work with are substrate ranges of enzymes, trying to predict whether an enzyme will interact with a substrate. I'm also doing a lot of database work of enzymatic reactions and trying to put it all together into designing cascades, enzymatic cascades on a computer, also doing some bioretrosynthesis and machine learning of reaction properties. There's also some work on uncertainty in machine learning. So what I'm really interested in is machine learning, deep learning, chem informatics, reaction modeling, software development, computer simulation, these kinds of things. So if you do want to collaborate, if you're interested in that, like, feel free to email me or stalk me on GitHub or on Scholar, and I'll be very happy to talk with you. And without further ado, I would like to start into the topic of today. And I'd like to spend the first hour talking a little bit about 2D and 3D similarity and how the electrostatic potential similarity comes in, what are the important topics you will need to know. So this will be about maybe 40 to 45 minutes. You'll have plenty of time for questions, and then we'll also go on to install the packages together that we'll need today. There'll be a little break, and then we'll do a hands-on workshop where you'll be able to follow along with me either on Google Colab or on Jupyter. So just to give you a quick preview of what we'll be doing, you don't need to do that yet, but just as a warning, we'll either use Google Colab. You don't need to download or install anything if you choose that option, but you do need to have a Gmail account. If you don't have a Gmail account, I will also show you how to do the same thing that I'll be doing in Collab in your own local Jupyter notebook installation. So we'll do all of that together at the end of the first hour. Also, if you don't want to do either of them, you can simply sit back, listen in, and you will still get plenty out of this workshop. So if we talk about similarity comparisons of molecules, what we would usually be interested in is how are these molecules similar? How are their properties similar? Do they react in a similar way? Do they interact with other molecules or biomolecules in a similar fashion? And what lots of people do is go for 2D similarity, because that is simple. Like, you only need your molecular graph And you can, for example, do a count fingerprint, which basically means that for each atom, you would look at its local environment. This is a circular fingerprint where, for example, for this atom, I would look at what the surroundings are. I actually have this surrounding 3 times. I have 2 times this fragment, once here and once here. And then we have those fragments here containing that chlorine atom. And then we could do the same for our nitrobenzene. And then we would see that lots of the fragments are the same and some are dissimilar. And we could construct a fingerprint that's just a vector representation out of that. Or we would, for example, count those environments and put that into a fingerprint, and then we could compare those. This is a very simple method of making a fingerprint. There are many more elaborate ones. You could also go for fingerprints that have some quantum mechanical properties or some properties that are collected from a database, and you could compare those. And this is a very good way of comparing the structure of a molecule, like the graph structure, but it's not so good to compare the shape. If you do want to compare the shape, you could simply put van der Waals spheres on each of the nuclei and try to compute the overlap integral between them. And you would also get a measure of similarity. In this case, it would be a little bit higher because here you've got nearly the same shape, whereas you do have a lot of fragments that are dissimilar. So your 2D similarity would be a little bit lower. But all of these methods only take into account the nuclei. So this is all about, hey, I'm a carbon, I'm surrounded by 2 carbons and 1 chlorine, for example, or I'm a chlorine, I don't know, I have a van der Waals radius of XYZ, and this is all the information you get when you use those similarity comparisons. So what is often neglected is all of the electrostatics. Well, the electron density. And that is actually something that as chemists is really important to us. So if you ask a chemist if these are dissimilar, he would probably ask, yeah, for what? Like, do you want to do a reaction? Do you want to introduce like groups in like ortho and meta para position? Like, what do you want to do with this? Because the electron density matters for that a lot. For example, nitrogen, this nitro group here, it has this mesomeric effect, this resonance effect, that it draws away electrons from your rings, which makes some positions much more amenable to some kinds of reactions and others not. And that chlorine actually has inductive effects and also some resonance effects. It's pretty interesting. And if we only go for 2D similarity or also for shape similarities, we don't see these effects. So we are quite limited on what our similarity comparison can do. So what you can do to take that into account is try to get a measure on that similarity. And you would, for example, if you plot those electrostatic potentials, just plotted them in the plane of these molecules, you see that chlorine is electron negative, it has some electrons, but it's like nothing compared to this nitro group here. It just draws away all of the electrons from your ring. So your electrostatic potentials look really different and the similarity is rather low. And the reason that I think this is important is because it's very useful to develop structure-activity relationships to also look at the electrostatic potentials and also the shapes. So if you think about a ligand that is bound to a protein receptor, what happens is, of course, you have some shape effects. It needs to fit into the pocket. It also has some covalent interactions maybe, and that really depends on the structure. There need to be certain atoms in certain positions. There might be some van der Waals interactions, which again depend on the shape and a little bit, of course, on the nature of the atoms. And there might be some electrostatic interactions, also some hydrogen bondings. So there are multiple different interactions. So if you really want to score that well, we need all 3 of them. We need the graph, we need the shape, and we need the electrostatic potential similarity. And once we know that, we can, for example, score how proteins and ligands interact. We could, for example, take one known ligand in, for example, its crystallized structure, and then try to compare it to a database of potential ligands to try to identify some that could also bind to the same target. We could also do a machine learning generative model and try to propose entirely new molecules that are maybe not even known yet that have kind of a similar function. Also, and that's a lot of what I do, we could score the affinity of an enzyme towards a new substrate. So if you know that an enzyme catalyzes these 10 reactions, would it also be able to catalyze that 11th one that looks kind of similar to the first 10? What you can also do, but it will not be the topic of today's talk, is you can use those scores to superimpose structures. For example, you could start with 2 molecules and put them on top of each other, compute your similarity scores, and compute a gradient, and then try to move around the molecules to get the best alignment. So this is also possible, but we're not going to do that today. And since I come out of that subset range of enzymes field of research, I just wanted to give you one example and show you what the current methods do and why that really falls short of how we need to describe enzymes. So if you think about this enzyme here, it's called hydroxyoxyglutarate lyase. You don't need to remember that name at all. But what you do need to know is it splits CC bonds next to hydroxyl groups. And it can do that for a kind of large variety of molecules. And what you see here is that there's one part that is always conserved. It is this part that builds pyruvate in the end. And then there's another part of your molecule which doesn't really matter what there is. So of course the hydroxyl group needs to be there, but the rest of this doesn't really matter. And if you look at how standard softwares try to score new reactions, they will usually go for 2D similarity of the overall molecule. So they will put in a new query molecule, just compute the overall similarity to all of these 3, and then try to judge whether that enzyme is also going to act on that substrate. And of course, this is not very accurate. There are also methods that say, okay, let's extract a template at a certain level of context, meaning that you will extract all of the reactive atoms, so all of the atoms that change their identity or that change their bonding status, and then some atoms surrounding that. And in this case, you will get 3 different templates for 3 different reactions, just because the changes in the molecules are so close to the reactive center. And this is also not a really good description of that enzyme, because it's just one enzyme doing one reaction. And as a chemist, you would see that one of the sides of the molecules is conserved and the other is not. So we spend a lot of time trying to make that better, just based on 2D. We decided that we wanted to construct CGRs, which are condensed graphs of reactions, which is just an overlay of the reactant and product graphs. And then we wrote a software to build so-called Hasse diagrams. And the reason I'm telling you this is because we'll use a Hasse diagram in the workshop later today. So you only need to remember that this exists. But it's actually very handy because it shows you all of the common substructures that you encounter in this set of substrates. For example, you see that it's always a carbon-carbon bond next to a hydroxyl group being broken. It's always, like there's always one carbon attached to that side up here that is secondary. There's always this ketone group here and this carboxylate here. And we get one most specific mutual template. So we would for once already have a template that is more helpful than whatever we had before, using standard templates, and we could also use that to score. And actually, if you look into the mechanism of that enzyme, you would see that this pyruvate side, which is conserved here, has some really specific interactions with the amino acids. And it's really important that it is there. Also, it forms a shift base intermediately. So this oxygen group, this one, is really important because it will actually form a covalent bond. And if it's not present, it's not going to work. So we do get kind of a lot of information from just the graph structure if we go beyond simple similarity and use those Hasse diagrams, and we build a software around that. It's called React. It makes those better reaction templates by building those trees, and then you can score a new query based on similarity. But again, this is just 2D similarity. It's advanced 2D similarity, but it's really, really missing that 3D aspect. And we already tested it on the 2D stuff, on enzymatic assays, and we see that it's a lot better in classifying between active and inactive substrates compared to simple similarity. There are some enzymes that are really selective. They won't work on a lot of substrates. So even if the similarity score that you get from 2D is really high, it will still not process that substrate. And our Hasse diagrams are better in doing that. But what we are really missing at the moment is some notion of 3D similarity, because as we said before, shape and electrostatics do matter, and we expect to get even better scores than we currently can. So what we did is we looked into literature and searched for available options for shape and electrostatics similarity. And there are a lot of good options available. For example, from OpenEye, you have ROX to compare shape similarity and Eon to compute electrostatic similarity. And you could either do that in solution. So if you want to have a solvent and maybe ions, then you do that via a Poisson-Boltzmann solver, or you can do that in vacuum, which would just be a Coulomb model. There's also Surflex, eSim, that is also based on electrostatic similarity. It also has some surface shape notion and some hydrogen bonding scores. And there's MRACE from AMD tools, which does that shape comparisons a little bit differently, but in a very clever way. And these are all really good options, but they're not open source. So you can get an academic license if you want to. If you're an industry, you have to pay for that license. And I think that really hinders the development of new models. And we really were interested into developing an open source solution for that. So that's what we did. We built this ESP-Sim Python package, which is built on RDKit. It is fully open source, it's freely available. It has a very permissive license. You basically can do whatever you want. So if you want to build a software on it and sell it, like, go for it. If you want to contribute to this and like send me a pull request to change something, please do it. Like, it's really a collaborative effort, and we are happy to get contributions. And what ESP-Sim can do is first align molecules, because of course, if you think about overlap integrals of your electrostatic potential, if your molecules are far away, the overlap integral will just be 0. So you need to put the molecules on the same spot before you can do any comparison. It has different integration routines for these overlap integrals that I'll talk about in a second. You have different metrics to compute similarities. You have different options for partial charges when we set up our electrostatic potentials, and you can also compare shapes. And we'll go through all of these options in a second. So let's talk about how to compute electrostatic potentials in detail. Like, ideally, we would work with the electron cloud. We would calculate overlap integrals between our electron densities. And that could depict really all effects like electronegativities and inductive and mesomeric effects and all of the other effects that you might be interested in. But it takes time to compute. We don't want to do a quantum mechanics computation every time we want to compute some similarities. So we instead decided to use electrostatic potentials to compare and not to compare the electron density itself. So that's the first approximation that we're making here. We're going from electron densities to electrostatic potentials. And then the second approximation that we're doing is we don't compute electrostatic potentials via quantum mechanics. We again try to approximate that, and we just use Coulomb potentials of trial charges to do that. That is actually a known method in literature. We didn't invent it at all. We just wrote a Python package around that idea. And this works well if you're comparing the electrostatic potential of molecules in vacuum. So there's no solvent, there's no ions. If you want solvent and ions, you need a Poisson-Boltzmann solver, and that's lots of work to implement, so I didn't do it yet. If you do want to implement it and send me a PR, I'm very happy to review it. But currently that's not available, so we just work with Coulomb potentials. Actually, there's one paper that says they're kind of the same if you compare molecules, so I'm just relying on that for the moment. So the idea is that we get our potential from just having charges of all of our atoms. So each of our atoms gets assigned a partial charge, and then we compute the distance from a trial charge, for example, that could be over here, to all of our point charges from a molecule to get an electrostatic potential at this very grid point. And then we try to integrate over that. Well, and integrating over something that has a 1/r dependency is kind of a bad idea, because as your distance gets closer, your 1/r function just grows to infinity. So first thing is, you can't integrate over that. Second thing is, it doesn't really make sense to integrate over that, even if you could, because then you just have the contributions of where the nuclei sit, and you would just get a score of whether your alignment is good or not, and you won't really get anything about your electrostatic potential. So what a lot of softwares do, also including eSIM that we talked about a little bit before, is to only compare those potentials outside of the van der Waals radii of the molecules, and then just evaluate that on a grid. They usually really do a grid comparison. They put a grid over like all three like XYZ coordinates and compute the values there. I personally think that for 3D that this is not a very good idea, and we use Monte Carlo integration instead, which is just a little bit faster, but it's equally valid. Or there was a very clever idea, which is already really old. It's from 1992 from Good et al., which said, well, we can fit that 1/r functions with Gaussians. And then you get that red curve over here, which kind of looks the same nearly everywhere, except from very close to the nuclei. And that's a region that we're not so interested in anyways. And you can just fit your function via 3 Gaussians. And then something really clever happens. If you want to compute overlap integrals, you have products of Gaussians and you need to integrate over them. And there's an analytic solution for that. So we don't need to do any numeric integration. We just do an analytic integration via a formula, which just saves us a lot of time. And if we visualize what this means, is if we just plot the raw potential, and I cut this at 0.1, otherwise you would have just seen like really, really small dots at the atomic positions. Then we see that the raw potential just really focuses on the position of the atoms, and you don't really see much else. If you fit that via Gaussians, you kind of get the same shape, but of course it's the magnitude of your function is much less, because this goes to infinity and this does not. So this would be computing your electrostatic potential via Gaussians, or you could just do the regular 1/r and just use that cutoff of everything that's outside of van der Waals radii you compute, and everything that's inside you just disregard. And then you have that area that you just don't compute and compare at all. So once we have those electrostatic potentials, we want to compute the overlap, because the overlap is the similarity between those two. And if you want to compute overlap between functions, so how similar, for example, is this function A to this function B, you want to integrate over them. So mathematically, this is an integration. If you just do that overlap integral, it will have a range that you can't really say without knowing the function. So you want to normalize this to some range so you can compare different molecules and you get scores in the same range all the time. And there are lots of different metrics, lots of different ways to normalize those integrals in literature. I just used the 2 most popular here, which are the Carlo similarity and the Tanimoto similarity. They have different ranges. So if you just imagine if your functions are identical, for example, 1, and this would be 1 and 1 and 1. So your maximum value is 1, and then the minimum value would be -1 if they're just the opposite of each other, and then 1 and 1 here again. So this ranges from -1 to +1, and Tanimoto has a little bit smaller range. And I sometimes get asked which one of them is better. Does it matter which metric I use? And it actually does. It does a lot, and it depends on what you're interested in. So if I have plotted those 2 functions, they are just potentials in 1D, and I integrated over them, and I put them through this Carlo metric and through this Tanimoto metric, and you see that you get completely different scores. So this plus here means that this is repulsive to a positive charge, and this is attractive to a negative charge. So there seems to be something that is repulsive here, so it's probably positively charged, and there's something negatively charged over here. It's like exactly the same positions, it's 100% well aligned, but the magnitude of this is very different. And with Carlo, you still get a score that is nearly 1, because these functions are nearly the same. And the Carlo metric is really insensitive to the magnitude of your functions. If a positive atom in your molecule 1 coincides with a positive atom in your molecule 2, Carlo will think this is very good. So this is a good choice if you want to compare molecules and you want to know whether, for example, the dipole moment points in the same direction, or whether it has a dipole moment at all, or whether the overall shape of your potential is the same, then Tanimoto is different because it also judges your magnitude of the function. So if the magnitude is different, then your Tanimoto score will be different. So if you want to compare molecules and you're interested in that the dipole moment have, for example, different magnitudes, then you don't want to go for Carbo because Carbo cannot see that. It will just give you good scores for everything. And then Tanimoto will be more descriptive. So it really depends on what you're interested in. And that I cannot tell you without knowing the problem. So just keep that in mind when you choose a metric. Also, please always report which metric you used, because otherwise no one else can really reproduce your work. Another thing that I would like to talk about briefly is partial charges. That's because we're using Coulomb potentials, which is just a sum of potentials that we get from point charges. So the nature of the point charge that we choose of the charge distribution will affect our results. And we did a little benchmark studies where we compared the charges and the electrostatic potentials from Coulomb calculations to different non-Coulomb partial charge distributions that are readily available. And we, for example, found that if you use Geiger charges, which are over here, which are the default in RD kit, that they are usually much smaller than charges you would get from Coulomb. That being said, like for Coulomb, there are also like 20 different methods to compute partial charges. There's like, they are different. There's no way of saying this one is better and this one is worse. We used RESP, which is a restricted electrostatic potential fitting method here, which tries to come up with charges that reproduce the electrostatic potential, which is good because that's what we're interested in here. We see that our range of charges that we get is much smaller than the one that we get from QM. And although we get kind of a good deviation between our quantum mechanical charges and the ones from RD-Kit, our Tanimoto similarity is really bad because Tanimoto cares for the magnitude. So if the magnitude is different, your Tanimoto score will be quite bad. Carbo doesn't care so much, so the score is quite okay-ish. You could, for example, also go for molecular force field charges. These are over here. They have quite a surprising correlation, to be honest. I would have thought it was worse before I saw the data. And you get quite good scores. We also have a machine learning model that we trained on Hirschfeld charges from QM. So these are different than the RESP charges. So they also have a smaller range, but they have a pretty good correlation. So you see that here, that we have a good correlation with that 0.85 with the Carbo score. But again, they are too small, so Tanimoto looks pretty bad. You could also go for something semi-empirical like AM1, BCC, and they have a pretty good correlation. So just keep in mind that the partial charge distribution that you choose will impact whatever score you see. It will not impact it a lot if you use only relative scores. So within a project, if you choose one, that's usually fine, but don't try to switch between different ones within a project, and always report what you have done, because otherwise other researchers can't compare to your work. Also, if you're interested in our machine learning charges, they actually perform really good in benchmarks. If you, for example, use ESP-Sim for rescoring .E targets or other benchmark targets, they come from a machine learning model. So I guess you all heard a little bit about neural networks, where they're basically universal function approximators. So what they do is they take input from some input vector, they do a linear combination of those inputs, they add a constant and pass that through some nonlinear function. That constant is important because it shifts your nonlinear function from left to right. And with a collection of those neurons, you can basically learn any functional dependence. So in that case, our functional dependence is what is my local environment as an atom, and our target would be the charge. So the way this works is you construct a molecule. We embed our atoms not by a fixed vector, but by something called directed message passing, which is basically a learned embedding of our atomic environment, where we start with some really simple embeddings, like, hey, I'm a carbon, I'm attached to 2 atoms, I have 2 hydrogen neighbors, I'm sp3 hybridized, and so on. And then we would exchange information via some layers of neurons, so some learned layers of those weights to get some elaborate atomic embedding, and that passes through another neural network to give our target. And we trained that on a very large database. So we did QM calculations of over 100,000 molecules. That's about 4 million atoms. It took very long to do that. These are quite high quality calculations, and we computed Hirschfeld charges. These are the fits that you see here from our QM targets to our predicted values. So the predicted values are on the x-axis and the computed values are on the y-axis. And we see we get pretty decent deviations, like 0.003. You might remember back from 2 slides before that our deviations to rest charges was like 0.1. That's because Hirschfeld charges and rest charges are not the same. So even if you do 2 QM calculations, you won't get the same charges if you choose different ways to construct the charges. We also trained on other targets that we don't need to worry about so much. But this work is included in ESP-Sim. So if you want to use those machine learning charges, they are available to you, and they are as simple to use as Geiger charges or any of the other charge distributions. It's just one click away, and we'll see it in the workshop later that they are really handy to use. So the last thing that we need to talk about is aligning. Well, because we are calculating overlap integrals. So if your molecules are really far away, the overlap will just be 0. And there are 3 options that you get if you use ESP-Sim for aligning. And the first one is unconstrained alignment, which really has no requirements. You can have molecules of completely different size and shape. It doesn't matter. And what this routine does is it randomly embeds a number of conformations for your molecule A and for your molecule B. Then it will align them via that open 3D align code from Tosco et al., which is built into RDKit. So it will try to align your molecules as best as possible. You already see here, if they're very different, it's kind of hard to judge where the best alignment is. And we also see this in the workshop, that this is a very difficult problem. And then it will try to choose that best pair based on either shape or electrostatic potential similarity. And you can do that on any molecules. Now, this is easy to do, but it may not be the best option depending on your problem. If you have molecules that have some common core and you know about this, then you should instead do a constraint alignment. And what that means is that some part of your molecule is always the same. And if it's always the same, it should always be on top of each other if you do the alignment. And the way we do this is we have some predefined coordinates of this core that we are going to create together today. And then we do a constraint embedding where we force these coordinates to be as close to the core as possible. They're not 100% the same, but they're pretty close. And then we again do a constraint alignment where we force these atoms to be on top of each other. And then we can choose the best conformers based on shape or ESP similarity, just as before. And the requirements for this is that you have some large common core that you know about. In some cases, it might make physical sense. We'll see an example later where we actually know about the binding site in an enzyme for its substrate, and we'll use that information to construct a common core. You can do that by hand. You can use any software you like. You can just do a maximum common substructure search, or you can use that React software that I mentioned before. And this is also why I brought it up, because we will use React in the workshop to give us a common core of a constraint alignment. And then the next thing that you can do is to just load aligned molecules that you have aligned yourself. For example, you might have a protein with some docked ligands, and you already have your 3D conformation from your PDB files. Well, in that case, you don't need to embed them again and align them again. You can just use them as they are. You will just compute one single value of shape or electrostatic potential similarity, and that's also viable with ESP-Sim. So the requirements here are that you know your aligned conformations, and you can make them with any software or approach that you like. So summing up, you have ESP-Sim that has all of these options. So you can align, you can integrate, you can compute the similarities. You have 4 different options for partial charges. There's actually one that I didn't talk about yet. You can also do QM calculations within ESP-Sim if you want to. We won't do that today. We will just focus on the other 3, but if you want to know how to do that, you can just ask me in the chat later. And you can, of course, also compute shape similarities. So this is all on GitHub, and I'm very happy to show you later how this all works. And you'll see this very simple to use. And just before going into that hands-on part, I want to give you a little bit of a glimpse of how ESP-Sim performs, because if it's just simple, easy to use, and all the results are crap, then it's still not worth your time. So we did a few benchmarks. One of them is an experimental study from Leo et al., where they actually tested about 500 compounds for interactions with the D4 dopamine receptor. And this is a really cool study because lots of the benchmarks that are on the internet for protein ligand interactions, they only have true actives, so known actives, and then they have a bunch of decoys of molecules that are thought to be inactive, but no one actually knows whether they are truly inactive or not. So there might be some false negatives in the data sets. And in that study, they actually tested those compounds. So we have true actives and true inactives. And then there's this really nice GitHub repository from Lewis Merton that I can very much recommend, that took all this data and rescored it with different scoring options for protein ligand interactions. And I won't go into detail into all of those. Most of those are actually scoring functions that take the structure of the protein, so they know the PDB file of the protein and the conformation of the ligand, and try to rescore that. That feature map vector is actually not based on a protein, it's just ligand centric, and it's a very clever way of scoring similarity that is built into RDKit. And you can see that our ESP-Sim method performs really well. We get a classification accuracy that is better than nearly all of the other scores. And it's also really fast. And it's like 100% ligand centric. So you don't need to know anything about the protein. You don't need the protein PDB. You don't need to know the structure. It is just comparing molecules, small ligands. The second benchmark that I wanted to talk about is StatE, which is the benchmark for protein ligand scoring. So if you work in that field, you will have probably heard about it. And we get a classification area under the curve of about 0.7. And if you look into this list, MRACE and eSIM, so those 2 options that I talked about before a little bit, they are slightly better. However, if the eSIM code also has hydrogen interactions, so if you take away those hydrogen interactions, you just score shape and Coulomb, we're actually pretty comparable. And we are better than lots of other packages like ROX or Vega, Optifor, NAMS. You might have heard about some of them. So with ESP-Sim, you don't get the best performance of all times, but you get a very decent performance in a very short amount of time. And it is open source. So I think it's a very valuable contribution to the field of research, and we really hope that it's useful to you. And with that, I'm nearly at the end of that first part of my talk, which is just the theoretical part. We talked a little bit about 2D, 3D similarity and electrostatic potential similarity. And I'm really excited to go into that workshop part with you. And since we have a little bit of time, I think we can take questions first, and then we can go on to install the packages together and then go into a break. So since I won't go back to my slides, I just want to give some acknowledgements to all of the groups I've been working with. And again, say, please contribute on GitHub if you have any functionalities that are missing that you think would be useful to ESP-Sim. Like, just write a issue at GitHub or write a pull request. I'll review it, and if it's good, I'll include it. And if it's not good yet, I'll help you to make it better. So there's really no, if you want to help, it's very welcome. And with that, I'll switch over to the workshop materials slide, but also take questions before that. that concern that first part of the talk.
Okay, there's a question from Simon. With ML learned ESP charges using DPMNN, does it account for intramolecular hydrogen bonds which may impact ESP charges? Even the 2D graph distance between the relevant atoms are far.
Yeah, this is a really clever question. And the answer sadly is no, because we are just looking at the local environments from the graph. So you won't have any 3D coordinates in that. It won't know that a hydrogen bond may be very close if that part is very far away in the molecule. But if we do go back to that part, you see that the partial charges are still very close to everything that we see in QM, and some of these also involve hydrogen bonds. So we don't get terrible partial charges for these cases, but they are a bit off.
Yeah. Can I ask a quick question? What do you do about potential tautomers?
So currently we just leave that up to the user, and we don't include any tautomers at all. I do have code lying around, but it's not in the ESP-Sim repo to try to canonicalize that and try to get the most reasonable tautomer. So if you're interested in it, I can send it along, but it's currently not in the repo. So it will just take whatever tautomer you present to RDKit, this will be taken. Also, if we compare that software, for example, to Eon from OpenEye, OpenEye will do rotations of the methyl groups or of like any terminal groups to get better alignment. And that's also something that we don't. So whatever the conformer is that we feed into a ESP-Sim will be the conformer that this comparison is run on. If you omit that like rotation part from Eon, and if you omit some other parts, like they compute pKa's and try to get the best charge state, if you omit all this, the scores from ESP-Sim and Eon are kind of the same. But
Okay.
that being said, Eon is able to do more, but they also have a larger team of researchers like working on it. So I unfortunately can't provide that option at the moment.
So, but you'd be willing to accept volunteers to help?
Yeah, definitely. So if you want to do that, and if you want to contribute, like that's very welcome.
Yeah. So there's a couple more questions. Excellent software, thank you. Curious about the different scalings of computational time with the number of atoms.
So that really depends on the number, on the integration routine that you choose. So if you go with Gaussian integrals, that is really fast because it's analytic. I think the benchmark that we did was like maybe like a millisecond per molecule, and the molecules were like of size, say 20 atoms, including hydrogens. We didn't do a real benchmark on molecule size, so I can only eyeball it now. I'll probably better do a benchmark and not say anything stupid right now. If you go for Monte Carlo integration, it is much slower, and it depends on the density of points that you evaluate. And I would say it's like a factor 10 to 100 slower than Gaussian.
Okay. Another question. How is ESP-Sim used to score or enrich active compounds from decoys in docking? How can this be done in a ligand-centric way without information from the protein?
So the way that we do it, and we'll actually, in the workshop later today, we'll score one of the .E targets. You would score a database of ligands. In this case, we have actives and decoys against one known ligand in its crystallized conformation. And then you would just rank all of your molecules based on the scores that you get from shape and electrostatic potential similarity. And we actually do get quite competitive enrichment scores. So we do think that this is possible.
Okay, thanks very much. I think that's up to date with the questions. Oh no, there's one more. I entered a bit late. Maybe Esther explained it. But anyway, why are you making training on Hirschfeld charges and not on RESP? And what you can use instead of Foucault index?
Okay, so That's something, that's a neural network model that we already had from a previous study. So it was not new at the time we wrote ESP-Sim. So we just included it as a convenience. I have actually RESP data for like, I think about 12,000 molecules. So we could retrain on that if we wanted to. I might do it at some point. So we do have that model, but it's currently not available in ESP-Sim just because we saw that this Hirschfeld charge model actually performed very well. It's like the magnitude of charges are smaller than the RESP charges, but as soon as you only do ranking, like if you compare different molecules and all of the charges are lower for all of the molecules, then your ranking order might still be okay. So the easy answer to this is because we already had this model. We might retrain it at a later point.
Okay, right, thanks. I think that you're up to date with all the questions now.
Cool. Then I think we'll just use like 5 more minutes or 10 more minutes, let's see, to get the installation done. And then I'll let you go to a break and stretch your legs a little bit. So if you go to, let me just bring up this last slide again, github.com, Ester ESP-Sim workshop, or you just scan that QR code. It will lead you to the workshop page. So again, github.com, Ester ESP-Sim/workshop. You will find this page here. It welcomes you to the workshop. And if you want to use Collab, you simply click on Workshop Collab. So if you click this will give you a little button of Open Collab, and you will click that button. It sends you to Collab. And what you can now see is a view of that notebook that I saved on GitHub. To make that editable to you, you need to save it to your own folders first. So you go to File and then to Save a Copy in Drive. So you click Save a Copy in Drive, and it says Creating a Copy. I will open it in a new tab. And what you will get is a copy of that workshop. You can rename it if you want, and you will be able to work on that. Google Colab runs on a Google server. So this doesn't run on your local machine. It means that we just use the server from Google that they gave to you for free to install the packages that we need. So we won't be installing anything on your local system. And also all of the files that we create will be saved on a Google machine and not on yours. So there's no installation, no download, no whatsoever on your system. You can also run this on your iPhone or like any smartphone or on your iPad. I just tested this today. So if you don't have a laptop readily available, you can just follow on any electronic device. The only thing that it will ask you is to log in with your Gmail. So as soon as you try to run a cell, we can try to run the first one, which will install all of our packages that we need, for example, RDKit, and then some GitHub repositories from my repo. If you run this, so if you click on this run button, it will say you need to log in if you're not logged in already. So I am logged in already, so it does all the installation. We'll talk about that after the break. But if you're not logged in yet with your Gmail account, you need to log in now. And that's because Google doesn't want a single user to run 100 notebooks at the same time. So they want to associate that to your account and just make sure that you're running one notebook at a time and not just taking down their entire system of servers. So that's Collab. So if you want to use Collab, that's the simpler option, then you just do that. If you don't have a Gmail address or you don't want to support Google or you hate Collab, then you can also instead install all of this locally. This would also be worth it if you want to reuse this and not like on your own system. And the way I'll show you today how to do this is just by creating a Conda environment. And you can just follow that little instructional on the GitHub page. So I'll just copy paste that to my terminal. It says Conda to create a new environment called ESP-Sim. and it will install RDKit, NumPy, SciPy, Matplotlib, and some other packages you'll need. So we just click OK on that. And I already have an environment, so I'll just rename that to something else because I don't want to overwrite my existing one. So I'll just call it ESP-Sim _test. And that will give me a new environment and download all of the packages. And once that is done, we will activate that environment and then just install those 3 GitHub repositories that I already talked about a little bit in Collab, and then we're nearly done. So this would be the second option. This saves files on your computer. So you're installing those packages on your computer, so you need some disk space for that. It's not a lot, but just for you to be aware of that. And also, once we run the notebook and we save files, this will be saved on your local system. If you use Collab, it will save the files on a server that is not yours. If you want to have those files, you need to download them. So this is taking a little while, but it should be nearly done in like 10 seconds or so. It's just verifying that it downloaded, it installed everything correctly. That looks very good. And we'll activate this environment in a second. Also, your computer might be faster than mine because mine is also running that Zoom meeting and sharing the screen. So I activate this environment, and then I'll just install those 3 GitHub repos. The first one, the ChemProp Atom Bond, is the machine learning charge model. If you don't want to use the machine learning charge model in your own research, you can just omit it. You don't need to install it. ESP-Sim will still run. It will just notify you that if you want to use machine learning charges, that it doesn't have it installed, but all of the other functionalities will run as usual, so you don't need to worry about it. I, in general, try to keep ESP-Sim modular in all of the imports. So if you don't want to do QMIC calculations, or if you don't want to do machine learning charges, you don't need to install it, because that's just wasting your disk space and your time, and I don't want that. So now we are installing the ESP-Sim package. That should be pretty fast, depending on my internet connection. If you don't have Conda, by the way, you can also install everything via pip. Just a warning, if you install via pip, it will just like change your local environment, and you usually don't want to do that, because if you have like some, for example, Python version, you don't want to change the Python version because of some of the dependencies of some of the new packages that you're installing. So it would be better to just make a local environment for that. There are tools to do that, like virtual env, just that being safe. If for Conda, you don't need to worry, because you're just creating an environment. If you don't need it anymore, you delete it, all of the packages are gone. You never need to worry about it anymore. So now that we installed everything successful, we can start a Jupyter notebook, but we first have to download it. So if you click on Workshop Jupyter, and you just copy that link, we can copy that. I just copy with like download with vget. If you do that, you just have to change blob to raw, which means that you download the binary files, not the compiled ones that you see on GitHub. And this will get Workshop Jupyter for us. If you've never used vget and you don't trust me that it's doing the right thing, you can also just go to the ESP-Sim main folder and click on code and just download the whole folder as a zip, and then also find the Jupyter notebook in the workshop folder. And now that we are done with downloading, we can type Jupyter notebook on the command line, and that will open our Jupyter notebook. You can click on Workshop Jupyter, and you have the same thing as in Collab. All of the rest is really the same. No matter whether you choose Collab or Jupyter, whatever you do, it is exactly the same. So feel free to choose whatever option you have. And I think we're ready for the break. And if you have troubles installing, then you can also use the break to let me know, and I'll try to fix it for you.
Okay, we'll take a 5-minute break now. Joshua, do you want to just say a few words? Liverpool Chem have really very kindly sponsoring all these workshops, and I suspect one on 3D structures is exactly what they were hoping for.
Yeah, thanks, Chris. Just to start off, I'd like to say thanks to Esther for the first half of the workshop. It has been excellent, and I'm really looking forward to the second half. So I'm Josh from Liverpool Chem. We are a chemical technology innovator on a mission to accelerate small molecule drug discovery through expanding access to 3D chemical space, as Chris mentioned. Liverpool Chem are proud to sponsor this series of workshops, as we do understand how essential these open source tools are for the global research community. At LCC, we specialize in using stereo-defined N-heterocycles for use in DNA-encoded libraries, fragment-based lead discovery, 3D, and we have our 3D discovery virtual library, as well as linkers for heterobifunctionals. If you would like to find out more information about how LCC could support your projects, please do reach out to us through our website, liverpoolcarachem.com, or find us on LinkedIn or Twitter. I hope you all enjoy the rest of the session, and thank you.
Right, thanks very much, Josh. So we'll be back in 5 minutes. Okay. Hi, then, Esther, do you want to start again with the workshop?
Yeah, sure. So just before we switch over to the workshop part, I also wanted to say that the slides, if you ever need them, if you want to come back to them, they are also in this workshop repository. So if you click on slides, you will be able to see them. Also, if you came in a little bit late today and if you want to look up some of the formulas or anything, you can just click on slides and just do that yourself. That being said, let's switch over to Collab or Jupyter. If you are on Collab, you still need to do that installation step. I already clicked it. And if you haven't clicked it, then click on the run button. It will download all of the packages that you need. It will throw a little arrow that one of the packages is incompatible, and we can safely ignore that for today. It will not impact any of the results that you will get. And from now on, this cell and the Jupyter cell is exactly the same, so you can follow along from wherever you want to. So we'll install a lot of packages from RDKit and also some to visualize our molecules. We'll import some functions from the ESP-Sim and the EHREACT packages. So again, ESP-Sim is for similarity scores, and EHREACT is for computing common substructures for our core. You can also use different packages for that. And then we have some miscellaneous packages that we'll also use. I also wrote a few convenience functions for you. You can just execute that first cell. The first one and the second one is to draw molecules in 3D and to draw these trees of substructures, so you don't need to worry about them so much. You probably won't need them ever again. And then I also wrote my own aligning and embedding function so that we can compare what ESP-Sim is doing by itself with something that we have written ourselves. And this might be useful to you if you ever want to write your own routines. This is about aligning and embedding, and we'll come back to it later. So the first example that I'd like to talk about is lactate oxidase. It's again an enzyme, and it is known to process those 9 substrates, and it is catalyzing the oxidation of a hydroxyl group that is next to this carboxylic acid. So it will turn that OH group into a ketone. And if you look at all the substrates, what you will see is that this carbon it is attached to is always secondary. It's always next to this carboxylate group, and the other side doesn't really matter. It can be aromatic, it can be aliphatic and linear, it can be aliphatic and branched, it can be really short or really tall. So there are different molecules that it can act on. And I just loaded those molecules. So I just drew these into small strings. If you don't know what a small string is, the super short version is it is just a notion of trying to get the connectivity of a molecule. For example, this one here would be a carbon, carbon, carbon. So this is 3 carbons in a row. These are these three carbons over here. Then we have one side chain. This is a bracket here. That is this carboxylate group up here. And then we have another oxygen attached here. And this just draws our second molecule here. What is really important is if you turn your small strings into a molecule, we do this with RDKit, this is the chem functionality from RDKit, you need to remember to add hydrogens because we are interested into 3D structures. And once we want to embed a 3D molecule, the position of the hydrogen matters. If you don't do that, you will get bad embeddings and you will get bad scores. We actually introduced a checking function in ESP-Sim because so many people forgot to add hydrogens. And then they reported back to me that they got really crazy scores and they didn't know why. So now we've got this check functionality in ESP-Sim that actually tries to prevent that. And I didn't get any responses in that direction ever again. So I think it was a good idea. So what we're doing here is just making molecules and just to demonstrate that if we make just one molecule, we made a list up here. I'll just copy paste one of those into a new cell just to demonstrate what RDKit is doing. If you draw one of them, then it doesn't have hydrogens attached to it. It knows where the hydrogens are. That is called implicit. So it knows the locations of the hydrogen just by counting how many neighbors an atom has, but it doesn't explicitly include them. And if you want that, you have to type chem at age. Again, this is really important for anything 3D. So let's try to compute similarities. So if these are the known actives, we should try to introduce something that we don't know yet, whether it's active or not, and try to score it. And actually chose two molecules, and we'll start with one that we know is active. So if you look up this enzyme, we will see that this probe molecule here is also active. I just typed out the smells and made a molecule with RDKit. I added hydrogens to arrive at this probe molecule. Now, if we just want to compute a score of electrostatic potential similarity and we don't care about anything, then this is really simple. All you need to do is use the embed align score function that we imported from ESP-Sim and fill in our probe molecules and all of our reference molecules, and we'll get back a list of shape and electrostatic potential similarities. And if you execute this, I actually forgot to execute the probe one. So you should execute all of the cells because otherwise it won't work. Oh, and I also didn't execute that one. I'm getting lazy here. Here we go again. Then you'll get a list of all of the shape and electrostatic potential similarities. You can also multiply those scores to get kind of a shape ESP measure at the same time. If you do want to multiply those, it is really important to renormalize your scores from 0 to 1, because the ESP scores, if you remember, Carbo is -1 to 1, Tanimoto is -0.3 to 1. If you do that and you have something negative and then a large shape, then it will be very large and negative, which doesn't make sense. So be sure if you want to have a combined score that you get via multiplying, that you renormalize. If you don't want to multiply them or you want to add them up or something, then you can just use the ranges as they are. So this is really just pretty plotting. The thing that we are doing here is calling this embed align score functions, and it really does everything for you, which is very convenient. It's just one function call and you get all the scores that you want. And we can inspect some of the embedded conformations. And I have to say here, we create conformers and then we align them. And once we align the next one, we override the alignment of the first one. So when I'm plotting here the different reference molecules, I'm really just plotting the last of each conformer, because otherwise they're not aligned because I've overwritten them. If you don't want it to override, there's a way to do it. But for our purposes, I just plotted the very last here, the very last conformer. I just fed it into our drawing function, which expects molecules. So we just give it a list of molecules. So it's always the probe molecule and then one of the reference molecules. And I just made a slider for us to select different conformers because it looks nice. But if you don't like sliders, you can just do draw and just say, I want to draw the probe molecule and maybe the first of the reference molecules, and then just draw that, and then you also get it. So all of this fancy notation here is really just getting that slider, but plotting one of them is really simple. And what we see here is we get an alignment that is mediocre. Like, it's not terrible, but it's also not great. Let's try to plot the second one. I'll just recompute this because it's, for some reason it got stuck. Here we go. Here's the second alignment of the probe with the second reference molecule, the probe with the third one, and so on. And we see that some of the alignments are pretty terrible. That's because we don't tell the program which atoms to focus on. So it will just try to align a very large molecule here, this reference molecule 3, with a very small one, the probe one, and it will just try to do its best to kind of overlay them. And there will be a better way to do it that we'll look about in a moment. But that's what you get if you just align without any constrainment. And we see that the best scores we get, they're like about 0.8 here, which is not terrible. And we could probably assume that this substrate is being processed if we would benchmark this against a list of known and actives and non-actives. But this is not the best way to do it. But it's very simple. By the way, if you ever need help with one of the functions, for example, the embed align score, you can just type help. All of the functions have very large stock strings that are very verbose, so you should be able to figure out what this is doing. It says it calculates a general alignment in the input molecules, and then it calculates shape and electrostatic potential similarities at the best alignment. It returns your shape similarity and ESP similarity, and you see that it has a lot of parameters that it takes. We just supplied the probe molecules and a list of reference molecules and nothing else. But we can, of course, change those options. For example, we per default made 10 conformers of the probe, 10 random conformers, and 10 random conformers of each of the references. And if you add more conformers, of course, you have a higher chance of getting a better alignment. So we can do that. So we had a default of 10 each. And we, for example, can now do 50. And if we execute that again, by the way, if you execute the cell as you are going along in the workshop, you might get slightly different numbers. And that's because the embedding is stochastic. And right now we didn't provide any random seed. And actually there's a pull request that will go online tonight that will fix this. So everyone will run with the same random seed and everyone will get the same scores. But right now it is stochastic. So you will get a little bit different embedding than I get. So you will get a little bit different scores than I get. And in general, if you use more conformers, you usually get a little bit better scores. But there is no guarantee, because we don't know whether we find a good conformation just because we add more conformers. We just have a higher chance of doing so. I also want to say here that the way the alignment works in this pre-made function that does everything for you is it will compare all of your conformer pairs, and then it will try to identify the one that has the best shape similarity, and just do one single electrostatic potential similarity on top of that. That's because of speed. Like, you don't want to do ESP similarity computations for all of your pairs if some of them are really bad. But if you really want to get very good ESP scores, you could do that. And there's an option to do it. It's get best ESP, which will actually compute an ESP similarity at each of the conformer pairs that we look at, which will be a lot because we have 110 conformers in each. So it will be 10 times 10, 100. And then for those 9, so we will do 900 computations. And we can do this and execute it, and it will, it's still pretty fast, but it took a little bit longer than the one before. If you actually run it on a local laptop, it's probably faster than if you run it in Collab, because Collab is sometimes pretty slow. And you see that we now get much better ESP scores at the cost of getting a little bit worse shape scores, because now we identify that conformer that has the best ESP similarity and not the best shape similarity. So you do get a little bit different scores. Actually, the conformers that I got when executing it today are really funny because the numbers are rather different. I executed like 10 times this week with other random seeds, and I always got scores that were kind of the same, but this time they're really different. So I think I got some conformers that are just really weird. So these numbers might look different for you. But if you're interested in doing ESP calculation for every of the pair, you need to set this to true. So we now see that the scores are higher in general, the scores are quite high, and we could think that this substrate is probably processed by this enzyme. We can also try this with another molecule that is probably not processed. So it has this hydroxyl group that is supposed to be oxidized, but the carbon here is primary, and we already saw from the reference molecules that it ought to be secondary. And then there should be this carboxylic acid group, and we actually have a methyl ester here. So it's kind of dissimilar from our other reference molecules. And if we execute the cell, we just call embed align score again with our second probe molecule, and again the same reference molecules, and we see that the scores are much worse than what we've seen before. Actually, they're really bad instead or apart from one. So we could probably assume that this is less well processed than the first query that we had. And in fact, if you look in the literature, the first one is processed, the second one is not. And if you would benchmark this, you would also find a good threshold of at which score you would discern between actives and inactives. Now, that was a very simple way to do it, but we actually know better. We can get better estimates of the alignment because we know the active center of each of the substrates for this oxidation reaction. So it's always this hydroxyl group next to this carboxylate that's being oxidized. So we can assume that these parts of the molecule really matter, and they are probably docked into the same position in the active pocket. So it would make sense to align with a constrained core that actually includes this reactive center, this constrained part of the molecule that is docked into the pocket. Now, it would be really cool if we had a crystal structure of the enzyme and one of the ligands in it, and then we could just use that as a constrained core, but we don't have this. We just have this list of smells, list of molecules that we know are active. So we need to create our 3D structure of the docked position ourselves. And there are different ways to do that. And the way I'm showing you today is with our React software, because I think it's very convenient, because it does all of the maximum common substructure search for you, and it also gives you some pretty plots. If you want to do this, we can just use this calculate diagram function that we imported from React, and we just give it this list of reference smells. We put the train mode to single reactant. It can also train on reactions, but we are not training on reactions. We're just training on single molecules here. And we can give it a seed, meaning that it needs to focus on this hydroxyl group. If we don't give it that seed, it will yield nearly the same results. But if we do know where the reaction is going to happen, it is meaningful to provide that. Actually, that function is computing a lot of other properties too, since we don't need any other properties because we don't want to use this for anything but knowing what our common substructure is, we can just set no props to true, which will speed this up. And if we compute this, it's also pretty fast, then we will get this tree. I also plotted it for you. It looks like this, which means that React finds that it's always this hydroxyl group, it's always a secondary carbon, it's always next to this carboxylate group, it's usually protonated. And then the other side is very diverse. It can be a branched aliphatic chain, a linear one, it can just end here, or it can be aromatic, and then the aromatic one can be substituted. It's always substituted in para position, and there are different substitution patterns. So we get all of this information, which is pretty cool, and we can use that now to find a common core. Again, you don't need to use EHREACT. I just think it's convenient because I wrote it and I know how it works. But if you want to use something else, like RDKit also has good maximum common substructure searches. However, if you want to do that, you need to rerun it for the list of references plus your query each time you add a new query. If you do the EHREACT one, you just run it once for the reference smells, and then you just need to query that tree. So you don't need to do maximum common substructure searches over and over and over again. So if you want to score, say, 1,000 molecules that you got from a database, EHREACT is probably faster than doing it with RDKit, because otherwise you have to recompute everything for 1,000 times. So in this notion, we find that the maximum common substructure is the secondary hydroxyl group next to this carboxylic acid. And this is also this node here that we see has no branches yet. So it's just a linear tree, and then it branches into different ones. So this would be the optimal 3D core that we used for embedding. But we can't just use that for any query because our query doesn't need to fit this pattern. And this is also where EHREACT is really convenient, because it actually has a function that is called find highest template, where you just pass in the root node, so the one where you don't have any structure yet, and your probe molecule, I just pass in the first one, and your diagram, so this diagram object, and it will find the highest template that is actually still working for this probe molecule, which is super nice because we don't need to do it ourselves. And if we run this for a different probe molecule, it will give us a common core for that probe molecule that actually has all of the atoms there that we need. So what we need to do now is to make up some 3D coordinates for this common core, so we can use it to do the constraint embedding and then do the constraint scoring. Now, again, if we had a docked position from like crystal structure, this would be great, but we don't. So we just need to help ourselves. And in this case, I just embedded the first reference molecule. So if this all chem embed molecule, I just create one confirmation of this reference molecule. I optimize it a little bit with a force field. So this is UFF optimized molecule call. And then I delete all of the substructures that are not part of this template here. And what we get is the score. I'm sorry, in Collab, the depiction of 2D structures, if they also already have 3D coordinates, is really ugly, but you have to believe me that it is still the same molecule as this. It just looks very ugly. But now that we have that core, we can actually call a different function, which is a bed aligned constraint score. So the difference to what we did before is that we now have this constraint embedding, and we provide again the probe molecule, our reference molecules, and the score containing the 3D coordinates that we just made. And if we rerun this, and I should probably execute some of these cells before, because otherwise this will not work. Then we'll get scores that are higher. So if we just look at them by score, they are higher than what we've got before. We got about 0.9, where we had 0.8 before. And if we inspect some of the confirmations, if we draw some of the molecules, you will see that they are much better than before. So what I did is I just drew all of the reference molecules on top of each other. I just redraw that for the confirmation that I have now. And these are 9 molecules on top of each other, so it looks really weird. But what we see here is that this part is conserved. So this hydroxyl group next to this carboxylate or this carboxylic acid is always the exact same coordinates. And then there's other parts like this ring or this aliphatic side chain that is somewhat different. So the constraint embedding gives you molecules that are aligned, that are embedded and aligned around this constraint core that we gave it, which is pretty nice. We can also, again, do the same plot that we did before with all of the single reference molecules. And we see that now our probe molecule here with the first reference molecule is really well aligned. Also, if we switch to the second one, it looks really nice. So we get much better alignments because we have input more information. Actually, like the information was all there, we just used EHREACT to process it. But we get much better alignments because we knew that this conserved substructure around the active center actually means something if we talk about docking substrates into enzymes. So we get those better alignments, and thus we also get better scores. Now we can do the same thing for a second probe molecule. And as I said, if you did this with RDKit maximum common substructure search, you would have to redo all the maximum common substructure search because you now have a differently sized molecule that might not have enough atoms to actually fit your common core that you see in your maximum common substructure search. So we again just run the template. We don't need to embed our reference molecule 1 again. We just delete other side chain substructures to get the core. And we see that the core is now really small. It just has this hydroxyl group. That's because in our template tree, all of our reference molecules were secondary carbons, and this one isn't. So the core it finds is just really small. And if we score this again, just with embed align constraint score, we see that the scores are still pretty bad. They're maybe a little bit better than they were before, but they're still poor. That's because this query is not processed by lactate oxidase. It just doesn't have the correct graph, and it doesn't have the correct electrostatic potential and the shape. Also, if you ever work with enzymes, you probably know that too little is usually worse than too large. So this should get bad scores. So this was one example of how to score substrates with constrained and unconstrained alignment, just using the native built-in functions of ESP-Sim. It's not writing a lot of code, it's just really simple to get those scores. The next thing I would like to talk about is how all of the different metrics and integration routines and partial charges influence your results. Because now we just use the default ones, which is Carlo, Similarity. It is integrating via Gaussians, and it's using Geiger charges for partial charges. And of course, if you change those options, you might change the similarity scores. And for that, I just used those two molecules that we talked about on the slides a little bit. So it was that chlorine and nitrobenzene. And I just called those embed functions that I wrote by hand with just one single confirmation to embed them. And if I draw them, of course, they're just in some random configurations. They're not on top of each other because I just embedded one random confirmation. They're not aligned yet. If you want to look at that function again, what it's doing, it calls that embedding routine that we also used before to create 3D coordinates of our common core. It first tries to embed the number of confirmations that we request via the regular embedding routines that RDKit has built in. And if this doesn't work, it falls back on a second routine that takes longer time to embed, but it's a little bit more stable for large molecules. So if you can't embed via the normal embedding routine in RDKit, it has some option, some way to still get an embedding out of this. I don't want to go into too much detail here because this is really an RDKit issue. And if you can embed it, it will throw and it will print a warning and return nothing. So we have our embedded two molecules, and then we need to align them, and then we can draw them again. So we see that once we align them, that this alignment is pretty nice. Also, this is an unconstrained alignment. It's just like what RDKit does when you call the alignment function. It's pretty good. And it is pretty good because the molecules are really similar. So whenever you have something where the alignment is easy because the molecules are similar, RDKit is doing a really good job. It is just that if your molecules are dissimilar or if they're very dissimilar in size, that you might want to go for the constrained core option, especially if the constrained core makes physical sense in your example. And what I did next is I just compute ESP similarity via this ESP function, and we can just inspect it a little bit before we call it. It's called get ESP-Sim. And if we do that, we see that it calculates the similarity of the electrostatic potential around two previously aligned molecules. So that's important. They need to be aligned because otherwise the scores will not be meaningful. And we again can provide our probe and reference molecule. Now this doesn't take a list. We want to provide one single reference molecule to get one single similarity score. And then there are lots of different options. For example, which charge distribution you want to have. This is called partial charge, and I'm blind. Oh, here it is, partial charge distribution. You can also just input partial charges via a list or an area of partial charges. If you already have them from like a quantum mechanics calculation, like you're welcome to use them. You don't need to recompute them. And then you have different choices for metrics and for integration routines. And then there's also some other options that we won't use today. Also, since we talked about explicit halogens, if you include this option, no check, you will not get this check, but it will speed up your code. I think there's a question, Chris.
Yes.
Since you
Can we use other program codes to generate conformers? Also, can we generate 50 conformers and optimize all of them and then pick the top 10 lowest energy conformers for ESP-Sim calculations?
Yes, so this is really the nice thing about ESP-Sim. You can just load conformers that you already have. You can, for example, use Omega or any other like program that creates and aligns conformers. And you can either like use them as they are. So if they're already aligned, you can just load them. We will actually do that in example 3. So if you wait a little bit, I'll show you how to do that. And you can also use like just load an embedded molecule and then align them with the function I have shown you like before. That's at the top. It's just an align function. You can also write your own align functions. There are also multiple different flavors of aligning molecules in RDKit. So you can do your own alignment and then just call this get ESP-Sim on whatever conformers you are interested in. And depending on the project, they actually do that a lot because the default ones in ESP-Sim, like the embed align score and embed align constraint score, they are great if you want to have a quick score. But if you are interested in something particular, you probably just want to do the alignment and embedding yourself that is like customized to the project you are interested in, and then just call that get ESP-Sim, and there's also get shape-Sim to get those scores.
There's an extension to that. Could you explain your choice of RDKit conformer generation over the other conformer options available in RDKit?
Yeah, so there's no particular reason that we chose that one. When we wrote ESP-Sim, we just Googled some of the options and we tried some. And that was the one that we found to be most robust and most like often used in literature. But you can use any other like alignment routine and embedding routine. There's like no magic associated with it.
Can I ask a question? I noticed that a number of the compounds had chiral centers, and yet smile strings didn't have chirality defined. Would you normally have molecules with the chirality predefined?
Yes, you usually like if your molecules are chiral and you know the chirality, then you should just include it. In this case, I just left it out because I was a little bit lazy when I prepared the workshop and I typed the smile strings. But in general, if you do have chiral centers, you should include them because otherwise RDKit will just do a random embedding and then you will get one out of the possible 0 isomers and you don't really know which one of those you'll get. So it is better to specify it if you know it.
That's all the questions for the moment.
Okay, cool. So what we'll do now is we have our aligned molecules. And again, if you just obtained them from any other software and you just loaded them into RDKit, and I'll show you later how to do that, then that is fine too. And you can call get ESP-Sim on that. And what I did next, I just tried all the different metrics, Carbon, Tanimoto, Gaussian, and Monte Carlo. and then Geiger charges, Merck molecular force field charges in the machine learning model. And we just run that. And we see that the Gaussian ones are really fast, and then the Monte Carlo ones, they are a little bit slower. And then we get all the different scores. Now, if you look at the scores, they are very different, but they do follow trends. So let's first talk a little bit about partial charges. So if you look into one block that has different, like same metrics and same integration routines, but different charges, we see that we kind of get the same scores. So they're usually very close to each other. And we actually found in our benchmarks that the machine learning ones usually perform best when you want to use this for docking, but the other ones are nearly as good. So concerning partial charges, as long as you use the same distribution for your whole project, you're usually okay, and you don't get very large variations between them. What we also see here that, for example, for Carbo, the variations that you get are less than, for example, for the Tanimoto one, because again, Tanimoto cares about the magnitude of the charges, whereas Carbo doesn't. So for partial charge distribution, choose what you think is best for your project and stick to it, and you usually be fine. For the other options, you have to be careful. So we already talked about Carbo and Tanimoto being different. So if you look at the Carbo scores, they are all larger than the Tanimoto scores, because Carbo just looks at the general function and its shape, and Tanimoto will judge the shape plus the magnitude. So the scores will always be lower, and that's kind of counterintuitive because the range of Carbo is larger. So you would think that the scores are larger, but they are actually the scores are smaller, sorry, by magnitude, but they are actually larger because Carbo is just less less discriminative when it comes to the magnitude of your function. And what you can also see is it matters whether you choose Gaussian integration or Monte Carlo integration. And that's because you look at a different region of space. So if we do the Gaussian integration, we really integrate over the whole space. So we integrate close to the atoms and very far away from the atoms, and we'll just average over that. And with Monte Carlo, we focus on one specific region that is outside of the van der Waals radius up to a box size that we can specify. And we'll specify that box size in a second, and you'll see that you get very different results based on how large you choose your box size. So takeaway before we do the box size thing is that the charge distribution really plays a minor role as long as you keep to the same distribution. And then Tanimoto scores are usually lower, and the integration routine does influence the results. So if we do that experiment and we just use different box sizes for that Monte Carlo integration, and we can also use different point densities, meaning how many integration points do we have in that numeric integration, and we run that again, and I'll just run it so you can see how long these take. So you see that the small box sizes and also the small point densities, they are rather fast, but then the large box sizes and the large point densities, they are pretty slow. So you need to balance accuracy versus performance a little bit, but we can already start talking about those trends within one box size. So if you have chosen one box size, the point density doesn't matter too much as long as it's not too low. So if you add more points to your integral, it becomes less noisy. So you usually converge to the same score as you add more points. In this example, we converge to 0.46 or here to 0.54. And as more points you add, the closer you usually get to this point. If we did 100, for the point density, meaning we have 100 points per cubic angstrom, we would get an even more accurate score, but it would also take longer. So the point density you usually don't have to worry so much about. Also, if you look at the higher box sizes, so if our integration box is very large, you can get away with a very low point density because you're integrating over a very large region and you're averaging over it. So the point density doesn't matter that much. But if you have a very small box size, meaning that you just focus on a region that is very close to the nuclei, the potential is very steep there, meaning that a little change and a little noise in your integration routine will influence your results a lot. And also you are focusing on a region that is like where the potential similarities are super different between different molecules, so your scores will be lower. So in general, the lower the box size means the closer to the atoms you compare your molecules, and that's causing the scores to be lower. If you have a very large box size like the 20 here, you average over a very large box size, and a lot of that space is really the same. If we walk back to that picture of that Monte Carlo integration here, if you make that box larger, you will have a region that is very similar. For example, you already see the edges here, they look kind of similar, but the points close to your surface, they are really different. So if you choose a large box, you will get better scores because you average over regions that are very similar compared to a small box. So that's something to keep in mind if you choose a box size. And that's something that you need to choose depending on your project. If you're interested in, for example, protein-ligand interactions, and you know the approximate size of your active pocket and your molecule, then you could adjust the box size to that region to really see what is going on in that region. And we also see here that the Monte Carlo integration is a little bit higher, gives better score than the Gaussians here. So that if you wanted to make them the same, you probably would have to choose a box size that is a little bit smaller. So the default is 10, which depends like on the size of the molecules and also on how strong the electrostatic potentials are, if that is a good approximation. So these are the options that you have. And especially if you choose Monte Carlo, you have to be sentient about the box size that you use because it will influence the results. Again, if you just want to use those scores for ranking, so for comparing different molecules, it might not matter that much. If you do want to compute absolute scores and compare them to something, it does matter a lot. So that brings me to my third and last example for today, which is stocking, which might be the thing that you're most interested in. And now that we already know how to use all of the functions in ESP-Sim, we can actually do that pretty easily. And I just chose one of the 102 targets from .e, and we will download this. So this URL lib request, we'll download this from the .e database. If you run this in Collab, it will save it to a Google server. If you run it locally in Jupyter, it will save it to your own laptop or computer. So we just download those, and then we open those SDF files, and we create the molecules from each of the molecules that is in this SDF file. So this, I think, answers the second part of the question that we had before. How do I use molecules that are already embedded or already aligned? You can simply Google how to open the file format that you're interested in. So in this case, it's SDF, but you could also use mol files or mol2 files or other files, PDB, for example, to save your files from another software, and then just open it in RDKit. In the .e case, the SDFs don't contain hydrogens. So this is why I call add hydrogens here, and I'm adding coordinates for the hydrogens. They are just guessed based on the location of the other non-hydrogen atoms. So I do that for the actives, I do that for the decoys, and I also do that for the crystal ligand. And once we've done that, we can draw all of our molecules. So this is the ligand that is bound to that protein in its crystal conformation. And as you see, we just loaded that from a mol2 file via an REKit function, and we made sure to add hydrogens. And this is our ligand in the doc conformation. And REKit does a pretty good job in adding hydrogens if they're not present in a file. So usually that's quite an okay approximation. We can also draw the actives and the decoys. I just again introduced the slider, and you can see we have a lot of actives, about 62. Also, I I didn't tell you all of the information. I didn't load all of the decoys because they are like 3,000 or 2,500. I just used 60 of them so that this benchmark runs fast and it runs fast in your system. You don't have to wait for 2 minutes to get some results. But this is just for this workshop. If you really want to score this, please use all of the decoys and not just 60. So we have all of our actives, all of our decoys, and they are already embedded. And .e, the like SDF files that .e gives you, they are not any like special confirmations of your actives and the decoys. They just embedded them with some software. So they don't make any physical sense. These are not like docked positions or whatever, but we'll just use them as if they were meaningful conformers, just to show you that if you made those conformers with a different software and they actually made sense, how you would feed that into ESP-Sim. But in this case, they don't really make sense. And I will show you how to do the embedding yourself at the end of this workshop. So in this case, I wrote my own aligning function just so that you can see how this would work. You could also just call the function that you get in the ESP-Sim package, but I just thought it would be neat for you to see what I do when I align molecules that are read from a file. And I just call that align function that I've written before. Basically, I look for the best shape, I align all of them, and once I've found the best shape, I align it again with that best shape, and I compute the shape and the ESP similarity with those functions that we already had before, get ESP similarity. And there's a get shape similarity that just works the same as the get ESP similarity one. And I'm using as a metric Tanimoto, and then I'm returning that score that I added up. We tried different versions of like adding and multiplying and renormalizing and probably like 10 different combinations when we did our .e benchmark. And I just found that adding them up really works well and you don't have to renormalize. In this case, I want to use the ML charges. And if you use the ML model, it does take a little bit of time to load the model. So if we call it for each of the ligands, it takes some time, so it's better to just pre-compute all the charges here. So I'll just run that and then pre-compute the charges. It will just take like 10 seconds or so to run the machine learning model on all of the actives and all of the decoys and also on the ligand. This will just speed up the computation. And then we can get all the scores by calling this align score function that we wrote on our molecule from this list of molecules, actives, and decoys, compare it to the ligand, and we will pass on these pre-computed charges. So if you have pre-computed charges from like QM, this is the way how you supply them to ESP-Sim. And then I also computed the area under the curve of the receiver operator characteristic so that we know how good we are here. And we get a score of like 0.76, which is not bad. Given the fact that we just used some random embeddings that .e gave us. But of course, this is not the best way to go because these embeddings are not meaningful. So we should probably try to add more conformers and then find the best alignment, not just the one that we got from .e. And if you do that, I again embedded 10 for each of the actives and for each of the decoys. And this line you don't really need. I just have it in my code just in case that any of the embedding fails. I throw away that molecule so I don't have any problems later on. I can tell you that there's 0 molecules that fails for this example, but it's just for safety and legacy reasons that this is in my code. Just beware of the fact that RDKit might not be able to embed all of the molecules, especially if they're very weird. So you see here, if we run this, that embedding actually takes long. It took like 10 seconds to do it. And now if we score that, this is pretty fast. Maybe not so fast today on, it is fast on my laptop. We get the scores. They took longer than before because now we had 10 conformers each. So we did 100 shape comparisons and not just one. And we, of course, get better scores. If you choose to use more conformers, for example, 30, all of this will take a little bit longer, and then you will get a better score, and we can run this while I talk. And the number of conformers is really something that you should like benchmark on. This is a hyperparameter in your model. You should try for your project of interest what a good number of conformation is. We found that like 10 to 50 is usually a good number of conformers for medium-sized ligands. It also depends on the size of the ligands. And now we see that embedding takes quite a lot of time. And I'm really sorry that I can't speed this up because this is an RDKit functionality, not ESP-Sim functionality. So this is not an ESP-Sim problem. So if we benchmark ESP-Sim and how fast it is, we usually only benchmark the scores, not the molecules. And in the interest of time, but I'm nearly done anyways. Oh, we're done here with the embedding. I can already tell you that the score gets a little bit better, but not much. And then we can also compute the accuracy. I just wanted to know what the optimal threshold was for accuracy. So at which point I want to discern between actives and inactives. So this is just what this code does, and it prints our accuracy of like 0.84, which means it's 84% of the times it classifies between decoys and actives correctly, which is pretty impressive. I have to say here, full disclosure, this is not true for all of the targets in .E. There are also some where this doesn't work at all, but also where other benchmark methods like MRACE or eSIM fail. So this was just by luck one that really worked out well, but there are also worse ones. You can also plot your scores of the actives and the decoys if you want to. I just made a histogram here, and you can see that the active scores are much higher than the decoy ones. And I think that also answers one of the questions that we had in the slides part today is, yes, you can use ESP-Sim to discern between actives and decoys, and it's actually quite simple. And with that, I'm at the end of this workshop, and I think we're perfectly on time. The summary is just for you. I don't need to read it out. So if you ever want to come back and think about in which example we learned, I don't know, how to compute ESP-Sim on, for example, pre-aligned molecules, you can just come back to this list and scroll up to the right example. Don't need to read through everything again. And with that, I would really like to thank you for attention. Like, reach out on GitHub or via email if you need help. And also, if you find this useful and you use it in your research, like, please cite us. This really helps us get funding for future research. So that will be very nice if you do that.
Yeah, that was fantastic, Ester. Really fabulous. One quick question from me. How do you handle the fact that some molecules could be ionizable?
So there was actually an example that I chose to omit because this was getting too long, where we actually made different tautomers in different ionization states first, and then we just scored all of them, and then just took the best one. And if you want to do something like this, there's actually a very nice benchmark that we did on this D4 dopamine receptor. So if you go to the D4 rescore benchmark in the ESP-Sim repo, this actually takes into account different conformers. And this is from this GitHub repo from Lewis Martin. And he actually shows you how to get those different tautomers and these different charge states. And then we just score all of them and get the best one.
Okay.
Which is maybe not the most elegant way to do, but it works.
Yeah, well, predicting pKa's of molecules is fraught with problems anyway, so it's probably the best way of doing it we have at the moment.
Yeah, exactly. Predicting pKa's is so tricky.
Yeah. We have no questions, so I think everybody's probably busy looking at your code and offering to help you extend it further, hopefully.
Yeah, that would be really great. Like, feel free to reach out anytime.
Yeah. So once again, thank you very much, Ester. This has been a real tour de force of looking at molecules in 3D structures and looking at electrostatics. I actually think it's absolutely critical for anybody who wants a job in drug discovery, so I encourage them all to look at this. I'll be editing the video over the weekend, and hopefully it'll be up on the CICAG YouTube channel next week. But once again, thank you very much for a fabulous presentation and workshop.
Great, thank you. You're very welcome.